All right, so today we're going to talk about Petz Renyi relative entropy, its properties. And, we were doing this last time. Excuse me. I'm slightly disorganized today. That's I forgot. All right. We talked about it last time, and we proved that it converges to the quantum relative entropy and the limit as alpha goes to 1. Right? So let me remind you of some things. That's relative entropy. Okay, that's how it's defined. It's a function of a density operator rho, positive semi-definite operator sigma, and a parameter alpha. Alpha is between 0 and infinity. The points in the positive real line not included are limits. You get them by taking limits. Petz Renyi is not known for alpha going to infinity. So the main points that we're interested in is alpha 0 and alpha 1. Last time we proved that the limit is alpha goes to 1. Recover the quantum relative entropy, which, just to remind you, lines like this. Okay. So that's a very important property, and this is actually the main reason that we're interested in this quantity. Okay, so we proved that last time. And now we want to prove some other properties, monotonicity and alpha. Okay, so we'll do that today. The alpha is monotone, increasing, monotone, non-decreasing alpha. And the other main one is that the data processing. This is true for every quantum channel n, and in particular alpha between 0 and 1 and 1 and 2. Okay. And then we'll get data processing for quantum relative entropy by taking the limit of this inequality holds, for all alpha in this range. We'll take the limit as alpha goes to 1. You get data processing. Okay, so we defined this quantity inside the law as the quasi-Renyi relative entropy, or Petz Renyi quasi-entropy. Okay, and we'll make use of this function. So one thing that's helpful to do is to rewrite it in a clever way. Okay, so we'll write that down. You write it as a sandwich function. Like this. So phi rho is the canonical purification of rho. It's square root of rho, tensor identity, and act on 1/share of the maximum entangled vector, gamma, right? So just to remind you, gamma, this. Right? So this is a purification of rho, that we've talked about. Probably did some of that in the homework exercises. What is f? F of x, x to the 1 minus alpha. Right? So why is that true? Let's prove it. We're going to make extensive use of this expression in the lecture to prove 1 and 2. Okay? To somehow make it easy. Okay, why is this true? So this is the definition. Okay. Then we'll rho to the half, rho to the alpha minus 1, rho to the half. Sigma 1 minus alpha. That's fine, right? Then we introduce gamma, right? There's this property of gamma that can be related to trace. So this. Identity, gamma, right? You see we're kind of getting closer, right? That's property of gamma related to trace. Now, transpose trick, right? We've used that so much now that you can guess it. We use this in Ullmann's theorem also to prove the expression for Ullmann's theorem. All right. Sigma we'll put as the transpose. Transpose minus alpha gamma. Now this is acting on a different system. This rho is the 1/2 can commute past it. Okay. So, and then this will be very close to the final rewrite. We'll do it like this. Right? And now you see the different parts, right? So we have phi rho on the left and right. So let's write that. Phi rho. And then these you can rewrite rho to the minus 1 so sigma transpose all to the 1 minus alpha on phi rho. And that's it. Okay. So rewriting this form is helpful for getting these two properties. Maybe there's other ways to prove it, but this is one way. Okay, so let's prove the monotonicity. So we're trying to prove here D alpha is less than D beta, or alpha less than beta. How can you prove monotonicity? Take the derivative with respect to alpha. And if you show that that derivative is non-negative, it's monotone, non-decreasing, monotone increasing. All right, so that's the plan. So plan, take the derivative with respect to alpha. Okay, so that will do, and use this form to do so. Okay, and here again we'll use natural logarithm, right? Because it's like we need to take a derivative, and we don't need to carry around an extra natural log of 2. Okay, so let's rewrite D alpha. Alpha minus 1 log quasi-entropy. And then we're going to abbreviate this operator. We're going to call it x. X to the 1 minus alpha. Because it's just a constant with respect to alpha. We're taking, we're interested in the derivative with respect to alpha. X equals rho inverse tensor signature. Okay. Oh, I should clarify that in this whole derivation, we're assuming that rho and sigma are invertible. You get the non-invertible case by taking limits. Okay, that's how it always goes. Or it's at least one way of proceeding, and it's somehow easier that way. Okay, we'll do another rewriting. We'll introduce a parameter gamma. We'll set that equal to 1 minus alpha. So this will be negative 1 over gamma log rho x to the gamma. And then the derivative with respect to alpha just is the same as the derivative with respect to gamma, but minus it. You got d alpha equals d gamma d alpha. Derivative of gamma with respect to alpha is minus 1. All right. So what does this mean? So that's what we're differentiating. And it's going to be a few basic steps. And then the plan will be to invoke the operator Jensen inequality to get the monotonicity. Okay, so we have to recognize some forms. Okay, so first step is simple. And yes, we have to take the apply the chain rule. Remember last time we said for an operator, we get x to the gamma log x. So the derivative can go. What do we do? This was a scalar. It's log of that, so 1 over that. And then we take the derivative of this expression with respect to gamma. Derivative is linear. We can bring it inside, differentiate this operator, and get this. Okay. Okay. Now we want to do a little rewriting. Yeah, so we want to have a common denominator. Whole thing divided by gamma squared. So that's just some algebra. All right. Now I want to take this gamma and put it through the log. That's fine, right? The gamma out in front with the log goes to the exponent. That. Gamma's there now. Okay. All right, and that is pretty much it. Why? So I'm just going to fill this proof now. So now we're going to set g of x, the x log x. That function is convex for scalars, but also for operators. So that was some fact that we stated in our math preliminaries a long time ago. Okay, so it's operator convex. Let's rewrite the expression as you can identify gamma here, or g of x here. So minus g x gamma phi. Yes. Plus phi rho g of x to the gamma. Right? And then, stuff on the bottom. The thing on the bottom is non-negative. That's the only thing that matters. Gamma squared is positive. So this, x is positive semi-definite because it comes from two positives. Actually, we're assuming positive definite. That's non-negative. So you should have to put here it's a bit non-negative. All right. Now we're basically set up to apply operator Jensen. So the claim is that from operator Jensen, what do we do? B dagger f of y, b is greater than f of b dagger y, b, where y is an operator and b is an isometry. Okay. In this case, the isometry is this sandwiching by phi rho. Why is it an isometry? Well, phi rho is a state. What do you need to be an isometry? B dagger B equals identity, right? But what if the input space is trivial? Then it's just the identity is the number one, right? So we're setting V equal to phi rho. And then B dagger B is phi rho, phi rho. It's a state that's equal to 1. Okay? So we can apply the theorem, right? We can apply, we're setting F equal to G, operator convex, Y equal to X to the gamma. Okay? And then, this right here is this one. And then this right here is this one. That's it. Right? So the derivative is non-negative. Is that all right? So just to review what we did, we wanted to show the monotonicity in alpha, vertical property of Petz Renyi relative entropy. It's nice to know that they're ordered, right? And then that implies the similar thing for Renyi entropies, but in the opposite order, because there's a minus sign. Anyway, okay, so what did we do? We said, use this identity, okay? Why was that useful? It somehow separated, like the original expression, you have alphas in a number of places, right? And so you at least have them in 2 places, is where with this approach, it's only in 1 place. Okay, so it somehow simplifies things. So we use this expression. we reparameterized alpha minus 1 as gamma. Right? Then we use the fact that the derivatives, we get a minus sign, derivative of gamma, derivative with respect to gamma has a minus sign when compared to alpha. So then, we use this. We simply took the derivative with respect to gamma, basic calculus thing, right? So it splits off into two terms, product rule. And then we found a common denominator, right? So there's this function here on the left, and we brought the gamma up to the exponent. Okay? That was the key thing. And then that was basically it, right? So we realized, oh, okay, this whole thing, if we say, oh, we'll define g of x as this operator convex function, we can finally rewrite that. Okay? And then at this point, it was a matter of recognizing that operator Jensen inequality applies. That was the core thing that we relied on. Okay? This statement here. We're going to use it again today to prove data processing. Okay? And then once we had that, it was a matter of pattern matching, right? So it was like realizing, oh, a state vector is a particular kind of isometry, right? We kind of said that thing earlier where we said, oh, a state is a particular kind of channel. Now, like a pure state is a particular kind of isometry, where we're going from a trivial space to a space with dimension greater than 1. And then it was just pattern matching. Right? It's like, okay, well, f is g, y is x to the gamma, phi rho is the isometry, apply operator, and that's in the dot. All right. Okay. So let's now move on to prove more things about Petz Renyi. I want to show you another way to write it. Okay. This was one way to write it. I don't know if you remember, but we had a formula for quantum relative entropy when there were spectral decompositions. And you could understand it in terms of a classical relative entropy. Okay. Similar thing can be done for Petz Renyi relative entropy. You can use the spectral decomposition and write it in terms of a classical Renyi relative entropy of particular probability distributions. So let's do that. I think I'll kill this side. We'll leave operator against. So we're going to derive another formula for Petz Renyi. Okay, so suppose spectral decompositions of rho and sigma, right, like this. Right, sigma index y is phi y. Okay. I was saying probability distributions, but more generally we allow sigma to be positive semi-definite. So Q of y is just a non-negative function. Okay, so let's substitute in the quasi-entropy. This is a pretty standard calculation. Okay. Now, if you use the functional calculus, function applied to a Hermitian operator is applied to the eigenvalues. Do that. In the interest of time, I'll just do it right here. Fine, right? Now we just kind of mix and match. Bring out the sums. Bring out the scalars. And the trace of this. So we're pretty much done. That's the formula. If we say that lambda xy is a joint probability distribution, remember this is the thing we did before. And mu xy is with q instead. Remember, the reason we could do this is if you think of this expression here as a matrix with these entries indexed by x and y, that matrix is a doubly stochastic matrix. That means if you sum over the rows, each row sums to 1, and each column sums to 1. And so it's a conditional probability distribution either way. You know, I think in physics that's called detailed balance. Okay, so if we make this identification, then we can do another rewriting as xy lambda xy to the alpha q xy 1 minus alpha, right? Because this part you can put in the exponent alpha plus 1 minus alpha, split it off into 2 parts. Okay, and then this right here is the quasi entropy. This is a classic. That's a lot of words. Classical Renyi relative quasi entropy. At least, Petz is not. All right. So that's interesting, and people have used that before in proofs. Okay, the reason I want to show you this formula is we want to prove that Petz Renyi is isometrically invariant. So this formula holds with every isometry V. Okay, and once you have this formula here, what is the answer to this? Well, I guess you know the answer, but let's say y is this formula, does this equality hold?
Because lambda and mu are invariant.
Lambda and mu are invariant. Yeah, right. When you apply the spectral decomposition, you get V dagger, the eigenvalues don't change. But as you identified, also this overlap doesn't change, right? Because you'll have a V dagger V in there. So it's like from this formula, you immediately conclude this. Right? In the book, we did it a different way because it's less straightforward for sandwich. There's some, we talked about sandwich Renyi relative entropy. We wanted to have like a uniform method for all the proofs. Okay. So that's nice that we get isometric invariance. That'll make data processing easier. We'll just have to show data processing with respect to partial trace. Okay. So, yeah, let's do data processing, unless there are any questions. I think I'll again just erase those, because I think it's helpful to have this cheat sheet here. So, data processing. So this, well, we said it. We wrote it over here. Right? This is what we're trying to prove for all alpha between 0 and 2. Why is it going to be only that range? That's the only range for which this function is either operator convex or operator concave. Right? The proof will give the proof for data processing for classical Renyi relative entropy as a special case. You'll get it for a wider range because this function is scalar convex for a wider range of alpha. But it's only operator convex or concave for this range. Okay, why is it useful to have isometric invariance for data processing? That means that it's, we just need to show data processing under partial trace. Right? Why is that? Just to remind you, we did it over here. So the way that it will go is like this. Remember the Stein-Spring dilation theorem, every channel can be realized by applying an isometric channel followed by partial trace. Right? So, and can be realized by, I'm going to write a curly V for the isometric channel followed by a partial trace over the environment. Okay. Then the way that the proof will go is, the first step is this, apply the isometry. And then if we have it for partial trace, we'll do this, trace E. And then that's the same as the final law. Okay. So this is data processing partial trace, some abbreviations there. Data processing under partial trace. Okay. So let's do that. And this is a lovely proof that Dennis Petz came up with, like 1985, 1986. There's a fair, it's the kind of proof where there's a fair amount of setup, but once you have the setup, it's one line, right? And the one line is operator Jensen equality. Okay, so we just have to like unravel a bit to get the setup, and then once we have it, it'll be one line. That's nice. Okay, so all right, so because of this chain of reasoning, it suffices to get this one, it suffices to prove data processing on partial trace. What does that mean? Rho AB, sigma AB, greater than the alpha rho A. This is for alpha 0, 1, 1. All right, so let's do the setup. You can use this formula, right? This gets reduced to proving inequalities between the Q alphas, right? Because what's in front is the same for both. 1 over alpha minus 1 log Q alpha. So it suffices to do this for Q alpha. So what we'll do is this. And this one's going to be for alpha 1 to 2. And then the opposite inequality for alpha 0 to 1. We'll only show the proof for alpha 1 to 2, and then 0 to 1 is the same proof, but using operator concavity instead of operator convexity. Okay. So we use this formula. We have a phi rho AB. This state vector here is a purification of rho AB like before, and it acts on systems AB and A hat, B hat, which are like, every purification have to have copies of the initial Hilbert spaces, right? So A hat and B hat are copies of A and B. Right, I'm going to define this explicitly. And then Q alpha rho A, very similar formula. Okay, so and then F is the same function we chose here, right? X to the 1 minus alpha. What is phi rho AB? That's a purification of rho AB. So we're going to have square root of rho AB and identity on A hat, B hat. This is the canonical purification. But now we need 2 gammons. Okay. So we're using the fact here that the maximally entangled state can split into a tensor product, right? Like suppose I have a 4-level, let me show this on the side. Okay. Suppose we have a 4-level maximum entangled state. I goes from 0 to 3. Then you can encode the integer I in binary, right? So let's do that. And all right, I'll just write all the terms. 0, 0, 1, 1, 1. So we did that. But now let's put system labels. So I'm going to call this C and C hat. Right? But C is going to be constituted by, C is a 4-level system. And there's an isomorphism between, a 4-level system and 2 qubits. Okay, so A and B will be 2 qubits. Okay, so then C will be, it'd be helpful to put the system label. Okay. The point is this: you can work with the algebra of the tensor product Okay. So just like a 4-level system is identified with 2 qubits, a 4-level maximally entangled state is identified with 2 e-bits. You can do these local isometries. What we're doing is this map. Originally I was represented as an integer, and we're just doing this map. We're making this identification. Integers to binary. That can be understood as a local isometry. And so we're doing that to get from here to here. I mean, technically, maybe we should write like this, isomorphic. But that's what we're doing. And so a generalization of this is being done here, right? We have these 2 systems, A and B. We need a purification. The standard thing, let me write it explicitly. Using this isomorphism, which generalizes what we wrote. And I believe this does get explicitly used in the proof. Okay, so that's where we use it. All right. Similarly, what is phi rho A? And now, I think we'll have plenty of time to talk about it. We said we wanted to apply operator Jensen. Okay, so we have to do so. We have to identify what is the isometry of B. What is it going to? What are the things that we want? Maybe I'll show you the proof. Maybe I'll show you the final thing first, like how it will go and the various properties, and then we'll go through the proofs of the properties. That might be more pleasing rather than to get kind of lost in details. So we're going to show the existence of an isometry that has this property. We're going to construct an isometry B such that B A take you to B A B A, and it'll take this state vector to this state vector. That's the key thing. Okay, when it acts on phi rho A, it'll produce phi rho A. Okay. Key property number 1, in addition to it being an isometry. Key property number 2 is that if it sandwiches rho AB inverse that it gets rid of the B system with this more complicated expression. So it's somewhat like it's somewhat playing the role of a partial trace, but it's not a partial trace. Okay. So we'll show that there exists an isometry with this property. Okay, very beautiful. Once you have that, you're pretty much done. Okay, why is that? This is what we want to prove, right? So let's write out the steps of the proof. All right, so I'm just going to copy this first line. Okay. Now let's use this first property that when V acts on phi rho A, it produces phi rho AB. So we can write this expression as phi rho A B dagger, F inverse, same thing in the middle, B, my row A. Now what? Remember the proof we said was one line. Thank you. All right. I know maybe you all know. Okay. So operator Jensen, B dagger goes inside. Now what? Apply this property, right? Excellent. Yeah, and that's it, right? So I said one line, but this is the key line, right? Operator Jensen. And then that's Q alpha. Right? So very nice. That's the proof Petz came up with. He originally wrote the proof with von Neumann algebras. And I don't know, it was good. Someone convinced them write down the proof for the finite dimensional case. And so they did that a year later. And it was very understandable to the common man and common woman of quantum information. So as a personal anecdote, I was very aware, I told you that I was involved in the invention of sandwich Renyi relative entropy. We were all very aware of this proof, but had no idea how to make it work for the sandwich Renyi entropy. And that was 2013. Then 4 years later, I figured out how to do a proof like this. It took 4 years, right? And then when you see the proof, you're like, oh, well, it's like the same proof. Anyway, so that's in the book. I don't think we're going to talk about that. Question?
So this sort of splitting of the gamma, that's sort of just like algebraic isomorphism between like g to the power of whatever can be broken into different products.
Exactly.
Basically.
Yeah.
So
it works for any product of dimensions.
right, but
yeah.
Specifically for we're using 2 as our prime, we're splitting it up into like 2.
Yeah, that's right. Yeah.
You explain like very briefly what a von Neumann algebra is and how I would use this in like an infinite dimension case?
Ah, very interesting.
Somewhere to read about it, I guess.
Oh, okay, thank you. So I mean, Petz himself has a book called Quantum Entropy and Its Use, and it does many things from the von Neumann algebraic perspective. So let me attempt this. When you go to quantum field theory, right, you no longer have states that have a trace, okay? And everything kind of switches to the Heisenberg picture, where you consider the operators. And you talk about, the lack of a trace is substituted by a functional that when you evaluate it for an operator, you get some expectation value. Right? And so everything shifts to these observables, and there are various things that substitute the notion of a state. Let's see. There's someone named Hagerup who came up with a notion that kind of plays the role of the density operator. This is my understanding. And so it's possible to do something similarly. This kind of rewriting is what Petz did in the von Neumann algebra case. Okay. So there's this thing becomes called a cyclic separating vector. Okay. And it's a way that you can write the Renyi relative entropy to states. You could say, oh, you said that there are no states, but there's like substitutions for these notions. Okay. And somehow this kind of expression, rather than using this construction with the tensor product, you use something called the relative modular operator. Okay, and we could have done this whole proof using the formalism of relative modular operator, but I kind of wanted to avoid that because like we can use these simple tricks that you learned about, like transpose tricks. That was the main thing. Right? So do you want to add anything to what I'm saying about von Neumann algebras?
Right. So this that comes in this algebraic approach to quantum theory, that rather than putting the emphasis on states, you put the emphasis in operators. So you have one harmonic oscillator, you have x, p, multiplication between them, a commutator, and conjugation, which is that. And that forms a C star algebra. And then the magic is that you don't even need a Hilbert space to make the quantum theory. States are just maps between operators, the algebra, and numbers and some properties. And then you don't even need a Hilbert space. You want to quantum theory with Hilbert spaces. And that is very powerful in quantum field theory, because in quantum field theory, there are choices of Hilbert spaces that are equivalent to each other. So DVD the Hilbert space, and therefore the best solution is to remove it. Really focus on the properties of an algebra. And it's also physical because operators will measure eventually. So you realize that the Hilbert space is a mathematical structure that you can get reference to. And it's very powerful. Think about the quantum theory.
I think another mathematical issue that comes up is you have a tensor product of an infinite number of Hilbert spaces, right?
Right, but that is not separable. So
That's not separate.
Yes, that was my thing. That was the main thing. Is like if I didn't theory, we can obviously decompose this to quite fine decomposition of the code. But then if it's infinite order, I know it's a game of infinite order split.
the Hilbert space is the focus space built out of a single Hilbert space, which is not a problem.
Right.
And it's
So
not
this
a-
can arise, right? Von Neumann algebras are helpful for handling this situation.
Right,
Am I
right.
right?
Right. The main difficulty in quantum field theory is that I mean, in general, you could build a Hilbert space, a focus space, and I could build another one, and they are unitarily inequivalent.
Hmm.
So there is no unitary equivalent. And there is that freedom. So what do you do? What do you formulate the quantum theory if there is that freedom? You can choose something, I can choose something else. We cannot talk to each other. The solution is to get rid of the Hilbert space. Focus on algebra.
There you go. Get rid of Hilbert space.
You can construct a Hilbert space out of a single state, a cyclic state. You give me a cyclic state, you could build a Hilbert space out of it using this GNS construction. And do it. Pretty powerful.
All right. What's a good reference for von Neumann algebras for quantum? Learning the basics.
Simple reference. I don't have any. I don't have any.
There are a number of tutorials I could pass along to. I would need to sit down and look up. Okay, so this was the proof for alpha between 1 and 2. We're using operator convexity. For alpha between 0 and 1, same thing, sign flips operator concavity. Right? Concavity is the same as convexity with a minus. Okay. So what is this amazing isometry that has this property and this property? Let's write that down. And in the remaining time, we can justify that part. I think now we can eliminate this stuff. Okay. So the V is this. I'm going to define its action on an arbitrary state vector. So size an arbitrary state vector. What it does is it'll tensor gamma on B systems. Okay. Then it will invert the square root by rho A. And then it will square root by rho A B. We could write tensor identity. Sorry, there's not root. Right. Implicit identity. Okay. So that's the isometry. All right. So first things first, is this an isometry? We have to show that, right? We have to show that B dagger V equals identity. All right, so let's do that. Okay, so V will be this. You're going to start suppressing identities. And then this gamma. Okay. This is its action on the state vector psi. Think of it as an operator, the psi is not there. Okay? And then V dagger is everything dagger. Inverse. So rho AB combines the square roots gives you rho AB. Right? This rho A to the -1/2 and this gamma, they act on different systems, so we can effectively commute them. I think it's helpful here to write the identities. I'm going to do that. Otherwise, you're a bit lost. What is what? Rho A to the -1/2 tensor identity on A hat. Rho A to the -1/2 tensor. Okay. Now what can we do? Yeah, this we again use this property, sandwiching an operator tensor with the identity. And this system gives you a trace. This realizes a trace over B. Rho. Let me write it explicitly. Trace over B, rho AB, and tensor identity. Right. Now what is this? This is rho A. Right? So this is rho A. So you have rho A sandwiched by rho A minus square root. That's identity. We assumed invertible. Right? So identity on A, tensor identity A hat. That's identity on A. Right? So, you know, we read this is B that was. So, you know, input space here is A and A hat. We showed that V dagger V realizes identity on A and A hat. So V is indeed an isometry. Okay. Perhaps the most unusual isometry that we've seen so far, but it's an isometry.
Is this a standard construction?
So in our research discussions, we talked about Petz recovery map. Okay? This is an isometric extension of a recovery map, a channel for recovering errors called the Petz recovery map. Okay? And Petz also came up with both things and used this in a different context for data processing. This is a standard construction. I don't know. What's standard?
So my question is because since V is supposed to take the extension of rho A, so purification of rho A to purification of rho AB.
Yeah.
So but rho A, psi rho AB is an extension of psi rho A.
That's not true. Right? This is a pure state. If we trace over B and B hat, we will not get this. Right? So the statement, okay, to clarify, rho AB is a density operator that extends rho A. When you trace over B, you get rho A. Phi rho AB is a state vector that purifies rho AB. So when you trace over A hat and B hat, you will get rho AB. Right? Phi rho A is a state vector that purifies rho A. So when you trace over A hat, you get rho A. However, the statement that you made is, it's like when you trace over B and B hat, you're tracing over this as well. Yeah, it doesn't work out. Right. So, but what we're doing is this isometry takes you from a purification of rho A to a purification of rho AB. Wait a second. Am I saying? No. I have not said anything correct. Okay, it is true if you trace over A hat, B hat, and B of this, you will get rho A. But if you trace over B and B hat, you are not going to get this pure state, right? So that's the only thing, yeah. But I believe that was your question, right? Yeah. Okay. Good. So it's an isometry. Why does it take phi rho A to phi rho AB? That you can kind of eyeball, right? I mean, we'll do it, but you see that like this vector will be embedded in here, and then you'll get a cancellation. These two, you'll be left with this in front, and then that'll be this. So let's do that real quick. B acting on phi rho A. This will just be substituting definition. B now. And then, something, the input of this isometry gets tensored by gamma, right? The input state vector. So it's substituted in rho A. Okay, so the point is we do this, right? Those cancel to make identity, and then you're left with rho AB. In this step, in this expression here, we omitted the identity. And this is the definition of phi rho AB. Okay, that works out nicely. Then what remains is this last thing. Okay. So let's do that. That's a few lines. dagger. All right, so we just substitute it. And again, omit lots of implicit tensor with identity. Okay, so this row AB to the 1/2 on the left and the right will combine with this to make an identity of A and B. Right there. Identity A and B, tensor sigma. We have okay. Now what? Similar thing to what we did up here. This gamma and rho A act on different systems, so we can commute them. I guess I will write the implicit identity on A hat. Okay, now there's a fairly subtle mathematical point to consider. When we write this transpose is always defined with respect to a basis, okay? With respect to an orthonormal basis. Here, it's a transpose on A hat and B hat, okay? And a full transpose can be realized as like a tensor product of individual partial transpose. If you choose the basis for the partial transpose to be the tensor product basis for gamma on A hat and B hat. Okay, so you need this subtle mathematical point for when you do the partial trace. Okay, so technically, let me write it here explicitly. This is a partial transpose TA and TB. This is it's a full transpose on A hat and B hat if that's what you're considering alone, and that can be realized as individual transposes. Okay, so we need that. You know, we're going to apply the fact that Soria's been telling us throughout. This is going to realize a partial trace over B hat. So with this structure for the transpose, it'll cleanly reduce to just the transpose on A hat when we take the partial trace over B hat. Okay, that was the only point I wanted to mention. And then this will nicely reduce to identity on A tensor sigma A hat T as a TA hat is the same as writing T here, because that's the whole system. Okay. And then everything collapses to the desired thing. Rho A inverse tensor sigma A hat transpose. Very nice. And that was the final thing we needed to the proof. Okay, we're pretty much at the time. There were other properties I wanted to mention about Petz Renyi, but that can wait. Any questions? So, yeah. But now that we have this, there's some interesting mathematical hoops to jump through, right? But we use various ideas presented throughout the course, right? It's kind of like many of the mathematical things that we talked about are here in this proof, right? Isometries, purifications, partial transpose, operator convexity, functions of operators, that kind of stuff. So, all right. So we'll see you on Wednesday.